Hello, this is Mr. White, and this video is on differentiating exponential and logarithmic functions with bases other than the natural base e. Here are our three exercises. So any textbook has formulas for exercises like these, but you know how I feel about just memorizing formulas without really understanding the underlying meaning behind them. So let's just quickly review a little bit of the Algebra 2 that's going to help us out in this process. With just a reasonable recollection of the definition of logarithms, if I were to ask you what's log base 2 of 8, you would hopefully say 3. And the reasoning is because 3 is the exponent that I raised 2 to in order to get 8. Okay, so if I now take this logarithm and make it an exponent of a base 2, then the result is, of course, 8. 2 to the third power gives us 8. So notice that over on the left here, we have an exponential function with base 2. We have 2 raised to the something power. And plugged into that, we have a logarithmic function with base 2. Log base 2 of something. And remember, logarithmic functions and exponential functions are inverses. They undo each other. They cancel each other out. So when you plug one of them inside the other, or into the other, they effectively cancel each other out. And we end up with just this 8 left over. And therefore, the rather obvious statement, 8 equals 8. Okay, if you bought all that, let's see where this is going to lead us for today's video. Of course, we recognize there's nothing terribly special about having used the base 2 here, so we can write a similar statement and have no trouble believing it, that e to the log base e of 8 is also going to give us 8. And then we see, okay, log base e, we know that's the same as ln. So let's write that as ln. And if I raised both sides to, let's say, the x power, well, this exponent, according to our exponential properties, just gets multiplied by this exponent. So we can rewrite it like this. And even though this 8 to the x may look prettier than this expression in the eyes of some, from a calculus perspective, this is a type of function that we already know how to handle. We know all about base e. So our general strategy for bases other than e is to take expressions like this and rewrite them like this and just use our knowledge and our skills about dealing with base e. Make sense? Okay, so let's go back to the exercise at hand. Here we have an exponential function with base 2. And as we just finished discussing here, before we even get into the calculus, we're just going to rewrite g of x. We're going to rewrite that 2 as e to the ln 2. And then that gets raised to the negative x power. And then the form that's going to be more useful to us is to multiply these two exponents and get e to the, let's say, negative ln 2 times x. ln 2 times negative x gives us this exponent. And now we've got our e to the u power format, where this is going to be our u. So let's proceed to take g prime of x, and we're focusing on this over here. And we know the derivative of e to the u power is just going to be e to the u, or in this case, e to the negative ln 2x times the derivative of u, times the u prime. So remembering that this negative ln 2 is just a constant. If we have, if we're taking the derivative of negative ln 2 times x, the derivative is just going to be negative ln 2. So keeping in mind that the whole purpose of converting to base e was because we know how to handle base e from a calculus perspective. We know how to derive and even anti-derive base e. Now that that purpose has been served, let's convert back to base 2. So looking at this expression right here, or really more specifically, looking just at the e and the ln2, ignoring the negative sign in the exponent, the e and the ln2 are going to give us 2, again, back what we started with, and we'll still have that negative sign and that x. We'll still have that up in the exponent. And we'll still have the negative ln 2 out by the side. And it's actually customary to put the constant out in front, so let's switch the order here. We'll put a box around it. If you want to, you could take that negative exponent, and you could also write this as negative ln 2 over 2 to the x power. That's another way you could write it, but you don't have to as far as I'm concerned. And there you have it. Let's check via calculator. We'll type the original function in y1 and the derivative as y2. For this one, I'm just going to use zoom decimal, zoom number 4. You can see that that's those window settings. And when I graph, I see the original function in bold, and it makes sense. We notice that that's a function that decreases over its domain. It's always got a negative derivative, so it makes sense that the derivative curve is below the x-axis. And I'll go to second calc, type number 6, dy over dx. Let's evaluate at, how about 1? And we see the derivative is negative 0.3466, basically. And I jump down, and I see that the output of the derivative curve is negative 0.3466. So we know we're in good shape here. Let's go on to the next exercise. Okay, similar concepts here. We will convert to base e, but notice we'll have a quotient rule thrown in here as well. I'll also point out that if you look at that 3 to the 2t, and if you really focus on just the 3 to the 2 power, you may rewrite that as 9 if you felt the need to, and then have that t still up in the exponent, all over t. I'm not going to do that here, but I wanted to point it out because sometimes our textbook will employ little maneuvers like that. But instead of doing that, I'm going to convert this 3 into base e. So we'll write it as e to the ln 3. And as far as the 2t exponent, I'm going to move that over a little bit. And let's put the 2 out in front and the t behind. And I don't want that to look like the ln of quantity 3t. So let's put some parentheses there just to make it clear. And that's all over t. So for deriving purposes, when we think of our e to the u, this is going to be our u function. And speaking of deriving, it's time to get into that quotient rule. So f prime of t will equal the bottom, t, times the derivative of the top. Now we're looking at that e to the u format, so we'll just do the e to the u, e to ln 3 to the t power, times the derivative of that exponent, times the u prime. So the derivative of any constant times t is just going to be the constant itself. So we'll write times 2 ln 3. So back to our quotient rule. That was bottom times derivative of top. Now let's do minus top times derivative of bottom. E to the 2 ln 3 t times the derivative of the bottom. And the derivative of t is going to be just 1 times 1 all over the bottom t squared. Now I should point something out here. The whole purpose of us converting to base e was so that we could, because we're familiar with deriving base e, and we wanted to make sure that we got the derivative of our u up there. We want to make sure that we got our u prime correct. However, when we're doing the quotient rule, for purposes of writing down our top function right here and right here, we didn't really have to use this version of the top function. We could have used this instead. So if you want, this is completely up to you. If you're comfortable with it, at the time of doing the quotient rule, if you wanted to, instead of writing that base e version of the top function, if instead you wanted to go ahead and just write the original 3 to the 2t power, you may do so. Just make sure that you get that u prime in there correctly. You'll recall in the last exercise that in the end we converted it back to the original base anyway. Okay, so Let's factor out the greatest common factor here. And it looks like up top, the greatest common factor is going to be 3 to the 2t here and here. So inside some big parentheses, we'll have, let's see, 2t, and then ln3 minus 1. And that's all going to be over t squared. And that is our derivative. That's about as much as we're going to simplify it. Admittedly, checking this one by calculator is a little bit more of a hassle, typing in that f prime graph, but here I've done it, and I find that these window settings work pretty well. Gives us this graph. Of course, the original function, f of t in bold and f prime not bold. And let's go to second calc dy over dx, number 6. Let's choose 1. We see that the slope is about 10.775. And if I jump to the derivative curve, it's off the screen. It's actually a little bit off the top edge of the screen, but I at least see the output value is what it ought to be. So we'll consider this one checked. And let's move on to the next one. So the first two exercises dealt with exponential functions with bases other than the natural base e. Here we have a logarithmic function with a base other than the natural base e. We're dealing with base 3 here. So to convert to the base e that we are comfortable with dealing with, we'll employ the change of base formula. You probably first learned this in Algebra 2. It says that when you have a logarithm of base c of some function u, that you may write it as a natural log of u over natural log of c. So we'll say ln of that x root x minus 1 over 2 all over ln 3. Now, it's customary in this context to simply write instead the top function times the reciprocal of the ln on the bottom. So that's what we're going to do. And this is also definitely a case where we'll want to take advantage of our log properties. So keep in mind, we're still dealing with the original h of x function. We haven't done any calculus yet. We'll make sure we keep that 1 over ln 3 intact outside of some parentheses. And then for the top, we'll say ln x plus ln square root of x minus 1 minus ln 2. That is simply our logarithmic product and quotient properties at work. And we know that this radical here could be written instead as an exponent of 1/2, which according to the logarithmic power property can be brought in front. So to recap, before we've done any calculus, we've employed our change of base formula and our logarithmic power, quotient, and product properties. Now it's time for the calculus. H prime of x. And all that prep ahead of time is going to help us out here because we're going to find the calculus is really quite simple here. We know the derivative of ln of x is 1 over x plus this constant out front. And then the ln x minus 1 gives us a derivative of 1 over x minus 1. That was this term, of course. And finally, the ln of 2 is just going to give us a derivative of 0. So the calculus step is done. Let's just do a little bit of algebraic simplification here. It wouldn't be the worst thing in the world to just leave this final answer as is, but we'll typically combine into a single term. So let's do 2x minus 1. We're doing the common denominator. 2x minus 1. And then over on the second term, we'll just do x over x. And up top, we see that if I distribute out, I'm going to get 2x minus 2 plus 1x. So 2x minus 2 plus 1x, that's going to give us 3x minus 2, all over that common denominator, 2x, x minus 1. And that 1 over ln 3, I could leave it on the outside, or I could bring it down here. Let's put ln 3. Let's put some parentheses there. And let's call that our final answer, h prime of x. So let's go ahead and check by calculator. I know it's a bit of a hassle, but I'm sure people from back in the day who, before graphing calculators, wouldn't feel very sorry for us. All right, here's in the calculator, I've entered the original function for y1 and the derivative for y2. I find that for this one, zoom decimal, zoom number 4, works well. That's the one with these window settings. And it's interesting to note that this is a case where we have a function, the original function in bold there, has a restricted domain. And we can look at the original function, and we see that due to the radical here, we can understand why we can't have x values less than 1. Yet the derivative function does not have its domain restricted in the same way. Anyway, let's go to second calc, number 6. Let's choose 3 this time, just picking that at random. And we find the derivative when x equals 3 is about 0.531. We jump to the derivative curve, and we see the same value. So let's consider this one checked.